Hi, George. Welcome to the Fireside chat in this virtual world. How are you doing?
Good. How is everything in Cambridge?
Yeah, doing pretty well. There's a ton of things to update you on, and looking forward to get some scoop of the latest and greatest from your side. So how
Great,
should we
yeah.
proceed? Should I start? Go ahead a little bit.
Yeah, actually, I was just trying to remember when we last met, right? It was probably when we worked at MSR with Nikolai, Nuno, and Gordon, right? We were trying to exploit these physical symmetries to scale data center verification. That was a lot of fun. But I think it seems like the latest work by Karthik and Nikolai seems to have really nailed the problem by this local contract stuff, right? So what do you
Yes, actually, the local contracts are amazing. All this stuff is deployed and as of now, actually a series of research projects that we've been working on jointly over the years actually now came to fruition, and there's all this stuff deployed in Azure.
Yeah. So tell me some of your latest stuff. I heard that there's some really cool things you're doing.
Oh, yes, yeah. So basically, what's going on right now is like you can say that finally network verification arrived in Azure at scale, and also in various parts of the network.
Wow.
So one thing that's going on is this runtime verification, where basically on daily basis routing tables are pulled from the devices and checked, and here this local contracts actually make this whole process to scale. This is the checking what's going on in production. There's a bunch of services that actually guard the data center networks from changes creeping in and causing outages due to misconfiguration. So actually now we have a bunch of services that where the network engineers upload change description, it gets validated, and if it passes the checks, again local contracts, then actually it goes into the production. And there was some actually huge challenges to solve to scale to the sizes of Azure data center networks or even entire regions. And and some of the latest things we've been working on is actually doing this kind of verification, but actually for the wide area network where we need to face the challenge of supporting the entire internet routing table and validate that. It's been pretty exciting. And
so it's challenging
there are
because
challenges,
it's really
opportunities, but I'm eager to hear what's up on your side.
Right. No, before you go there, of course, you never find any bugs, right? Azure configs are always perfect, correct? Just teasing. Don't answer on the grounds it might incriminate you, right? But tell me, the problem is what is the scale of this wide area thing? It's how many prefixes? What kind?
So basically, yes, it's a very good question. So you can imagine that what we care about. For example, we want to verify that this very rich and complex peering policies, how Microsoft peers with the rest of the world, actually behaves well when this peering policy is adjusted, which happens all the time because of the relationship. And you can think of the wide area network receiving advertisement pretty much for everything that's active on the internet.
Wow.
And if you take if you zoom down into prefixes that are actually carrying some flows, basically there's some traffic. So think of like 500,000 prefixes. And then you say multiply it by a factor of 10 or higher, because every single prefix is actually advertised on multiple locations. Then you come to millions of AdWords that you need to track during the verification process.
Wow. So could I think of this as, like I think there were these early simulators, high-speed simulators like Batfish. Could I think of this as a really simulator on steroids that can, when you make some changes and announcements, it can quickly simulate the changes in all the routing tables?
Exactly. Essentially, in a sense, Batfish pioneered this idea of having high fidelity simulator that understands all this protocol. And what we did for Azure is we'll build a simulator that's specifically tuned for performance and for the protocol features that are relevant for Azure network configurations.
Makes sense.
And with very careful algorithmic engineering and data structures and everything optimized for performance, actually, we managed to scale to this amount.
That sounds great. But there's still scope for verification in the wide area, correct?
Because we are just scratching the surface. So basically, there is a ton of work, and where sort of combinatoric hits us and sort of we have absolutely no good idea how actually to proceed is, what if you want to check resilience of the network against faults? So if you take down one link, and sort of there are so many thousand links to take down. And imagine you take 2 links, and now it's a quadratic combination. How to deal with that, no one knows.
Got it.
So maybe you have ideas.
Well, yeah, we do have a few, but okay. So let's see. So would you like me to tell you a little bit about what we've been doing at UCLA?
Oh, that would be awesome.
Okay. So first of all, I just want to say that a lot of our work at UCLA has been with my colleagues, Todd Milstein and Yuval Tamir, and your own colleague, Ryan Beckett, and 2 students, Siva Kesava and Alan Tang. Siva is graduating, and I hope you guys will interview him. Okay, that's a plug for him. All right. So one of the things we've been worried about is that we feel that network verification has made a lot of progress in scaling, like your work, but data plate verifiers now scale to large data centers. But 2 important usability problems remain, right? So the first is the lack of specifications of desired network behavior, right? And the lack of localization. So you see there's a bug, but you would like to know in a 20,000 line config, which 10 lines were the problem. So we are excited about 2 open source tools, Campion and Self-Starter, that tackle these problems in different ways. Underlying both of them is something I think you're fascinated by, which is modularity. They make a modularity assumption that config modules within similar routers should be similar. So this is modularity within the box. I think, we need to go to modularity outside the box, right, in order to scale the wide area. But anyway, so what Campion, spearheaded by Alan Tang, it verifies sort of a very common requirement that 2 routers like backups are identical semantically. So backups with different manufacturers is somewhat rare, but it happens. But more interestingly, we found in Alibaba that sometimes people take a Cisco router, which has a config, and then they replace it with an Arista router, which has a different config written manually. And they're supposed to be identical. And they get it wrong, right? And so what we did there's no need for a spec because the previous guy is the spec, right? And we perform localization by checking equivalence modularly on corresponding pairs, and then we do a pairwise semantic check to isolate the right lines. And so on the other hand, this tool called Self-Starter that we have, right, it basically identifies network misconfiguration without a spec through a kind of novel form of outlier detection. It assumes that everybody at the same level of hierarchy in a data center is roughly similar, but so it kind of assumes the majority is the spec, right? But of course, there are intentional differences, like we found in the symmetry stuff we worked on together. So the tool automatically infers parameterized templates, right? And so it models the intentional differences as variations of the template and models errors as variations across templates, right? And now textual localization comes immediately because, just look at the template, the patterns that are different in the templates, right? And so they're very different. Self-Starter assumes that things are meant to be structurally similar, and so it needs syntactic similarity, same config language. Campion doesn't assume that, but it has a more limited kind of use case, right? Replacement or backups. So both tools have found significant use in the Microsoft and Alibaba clouds. And more generally, we hope that people will start thinking of how to deal with no specs and a lack of localization. Okay.
Oh, wow. So that's very exciting. So there is something actually I wanted to bring up, and I think sort of this is a topic that you mentioned sort of in the past. We talk about network verification. It's a kind of has some universal touch to this statement, but in fact, if you look over the years, first by network we meant the the forwarding plane, then we expanded to the control plane. Now these projects that you just described actually looking at the configuration as the first class objects in the under scrutiny, But still, if you think about networks, there's just so much more. Do you think there's maybe a little bit of mismatch and there's something you need to do going further beyond? So what's your thought?
Yeah. So first of all, I think you and I agree that term network verification, and I'm probably slightly at fault for popularity, is bad. It's a bad name because we really verify only the configs, right? We don't verify the protocols, BGP. We don't verify the hardware. So it's a bit of a joke, but nevertheless. But yes, so during Siva, the students' MSR internship, right? Ryan Beckett led him and us to considering DNS, for example, along with Benaz. So basically the observation, I think it comes from Jitu, was that even if the routers work, if DNS fails, the network is dead. So I think this is your point, right? So the first approach we did was called GROOT, which is a SICOM student paper award for Civa. It verified the config files in DNS that are known as zone files, right? And as with some approaches to network verification, it showed that you can verify properties across all queries, and it did that by computing equivalence classes. The only technically different thing from network verification was the algorithm, instead of being quadratic, is almost linear because it exploits the tree-like structure of DNS. So it has found some bugs in Microsoft and Akamai, and but not the most serious ones. But Civa is trying to apply it at Amazon this summer, right? And it's probably great for finding bugs in customer zone files, but those are really hard to work on because of confidentiality. But Civa's next tool, Ferret, does some testing for DNS implementations, and it has found it's very different. Not the zone file, and it's not verification, it's testing, but it really scales to these large DNS name server implementations like Bind and Power DNS. So the idea is kind of an interesting one, right? It basically goes ahead and it's not quite symbolic testing, it's not fuzz testing, it's something we call scale. And I'll let if anybody's interested, I'll tell you more about it later. But it makes this small scale assumption. Scale stands for small scale, constraint-driven automated logical execution. It's too long to explain what's going on, but it's found a lot of cool bugs. It's found a lot of cool bugs in Bind and Power DNS and big-time name servers. Okay, so sorry, long. So by the way, just hire Civa and MSR, right? I think
you're amazing. Sort of, it looks like you are. Yeah, so you're amazing leader and sort of also amazing university professor, sort of bringing sort of this new generation of researchers. To the
and
world.
Alan is doing well too. So
No, this is cool. So one thing actually, sort of we are getting close to the sort of to the end of the allocated time slot. But sort of what I'm curious about is that sort of things that we sort of touched upon is basically sort of verifying an artifact, like routing table or config or whatever, sort of actually after it was created, sort of. So should we invest more into sort of designing tools that will basically allow us to build artifacts that are correct by construction?
That's right.
So what's your thought on that?
Yeah. So at UCLA, our group is called the Network Design Automation Group because we're less interested in verification as the broader thing of applying language tools, right? And you as a language person knows that compilers, of course, are the way you go. And this is crazy that we write these manual. So I think progress at that has been very, very hard. And there are some reasons for that. But I think beyond that, debuggers, right? We need debuggers. And some people, we also might want to use, so we've been trying to do some debugging of clouds like Azure, where it's not just the network, it's the system as well, using machine learning. And some folks at USC are trying to use other kinds of interesting techniques like natural language processing to take these, either these logs that people have for false or the RFCs, which are textual documents, and make them machine executable, right? So there's a lot of cool stuff going on. And part of it is, as you said, expanding beyond the network, but also applying different tools like machine learning and natural language processing. Is that a long answer?
No, I think sort of So actually, I'm always amazed how sort of this field is expanding sort of. And I remember sort of initial sort of presentations basically saying, there's all this work in sort of program verification and sort of what if we were apply these ideas into the world of networks, because by the end of the day it's all sort of compute and communication sort of, and you can have sort of formal underpinning and analyze the models and but sort of now how this field is expanding, sort of I think it's breathtaking. So we are I think sort of it's been a great chat. So I've learned a lot, sort of, and there are some exciting sort of ideas to follow up. And so I will call you up later. And sort of thank you very much. I've had a great time.
No, it's great to see all the cool stuff you've been doing at MSR too. So, of course, I always have a fondness for Microsoft, having worked there. But very good to talk to you, and my very best to your family. Okay, take care.
Thank you. To yours too. Bye bye.